This video is going to talk about graphing polynomials. And in order to graph polynomials, there are just certain parts that we want to be able to use to make a simple sketch. Again, if we want a lot of detail, we can always use a calculator. But again, a simple sketch should be enough to kind of get the basic idea, get some of the major parts to a polynomial. So you'll notice up top, we've got a polynomial. Now, mind you, this is sort of in a, not an expanded form, it's in a factored form. You could always multiply everything out, get rid of all the parentheses, do a lot of distributing, and you'll have more of a, what we think of as more of a standard form of a polynomial. But this will get us by with enough evidence, enough information to help us out. So down the left side, we've got a few things of information. So we're going to want to be able to use what we call the end behavior, the x-intercepts, the multiplicity, which is very important, and then extra values as needed. So let's talk about what each one of those four are, and then we'll come back to this problem a little bit later. First of all, we just want to remind ourselves x-intercepts are also called zeros and roots and solutions. Those are all really names for the same thing. X-intercepts do need to be real, whereas the other three can all be imaginary. But all of them basically come down to saying if we have a function f of x, again, x equals a is a zero of the function, right? If a is also a solution to the polynomial when it's equal to zero. And again, if it's an x-intercept on the graph. And again, roots is just sort of an older name, but again, all of those things sort of mean the same thing. One other connection we want to make are factors. Again, if we have a zero, like let's just say x equals 2, it would be one of our zeros of our function. Therefore, our x-intercept might be, 2, 0, right? Saying that y equals 0, because that makes an x-intercept. Then the factor will be that x minus 2 would have been equal to 0. And you can kind of see that connection. Again, add 2 to the other side, or basically if we subtracted 2 on this equation, we'd get right back to x minus 2 over here. So again, that connection between a zero and a factor. All right. Now, as long as we're talking about zeros, we also want to just mention very quickly, there is a theorem called the intermediate value theorem. Now, it's fairly basic, but if you're ever using your calculator and you're trying to find zeros, if you're looking at the table, the place you're going to want to look are at the y values, because in order to get from negative y values to positive y values, we have to cross 0, right? If we picture it on our graph, in order to go from positive to negative or negative to positive, we have to cross 0 somewhere in between there. So if we're looking at a table, I'm going to look for anywhere the y values switch from negative to positive or positive to negative. But we're not going to identify it by that. Again, we're looking for the x-intercepts because we want to know what the x value is, not what the y value is. So if we're looking for an interval where there might be a 0, in between these two numbers, again, is a 0. So in between -1 and 0 for x, we would find an x-intercept. Same thing from 5 to -12, right? We switch down into the negatives. So therefore, between 0 and 1, right, in the x values is where we're going to find that 0. And somewhere in between, again, -21 to 50, notice we've got to cross back over that 0. So somewhere in between 2 and 3. And if we actually did go find them, again, maybe use our calculator, second calculate the zeros, do a little left bound, right bound, we could actually find those numbers. But if all we're doing is looking for some intervals, right, the intermediate value theorem just says between these numbers, I'm guaranteed because we went from positive to negative, in between those, somewhere there will be a 0, right? So just good to mention some theorems in math here. Now, a couple other details, things we want to think about. The degree will definitely help us graph. If you notice up top here, we have 3 different x's all being multiplied. So therefore, the highest term in this thing is going to be an x to the third. Therefore, we're of degree 3. If you remember an old rule, if it's cubic like that, then it might have a bottom point and a top point, but at most, 1 minimum and 1 maximum. Or the maximum number of turning points is always 1 less than the degree. If this was degree 6, we might have up to 5 turning points. Because it's degree 3, we can only have up to 2 turning points. That way we can still end up with the right end behavior. All right? And we've talked about end behavior before, but again, that's what this leading coefficient test talks about. When will we know? How did we know that this end would have been going up And on the right side, we would have been going down. How do we know we're rising to the left and falling to the right? And again, that comes down to the fact that, again, we're cubic, right? We're third power, which means the two ends have to go opposite ways. Normally, a cubic function, positive value in front of it, would go down to the left and up to the right. But because we have this -2 in here, our leading term is going to be a -2x cubed. Therefore, we're going to rise to the left, and we're going to fall to the right. And that's how we kind of know those things, right? We're looking at that leading coefficient, and we're looking at that degree, right, at the same time. Odd degree, opposite directions. Negative means we start lower left, we go to the upper right. And then finally, the zeros. The zeros, it's kind of nice. We have all of our different factors. As I mentioned, we have 3 different x's, 3 different quantities here. So we know we'll have zeros at 0 for this one. Because if I plug in 0, x is 0. 0 times -2 is 0. 0 times those 2 quantities will be 0. 0 times anything is 0. So therefore, we're going to be at 0, 0. And you'll notice we had that in the middle of the screen. Here, if we plugged in a 3, right, if x were 3, this factor is going to end up being 0. And again, it's multiplied by everything else. So 0 times everything means that's going to be a 0 of my function. F of x will equal 0. And if x were -1, again, f of -1 would also come out to 0, right? This factor over here. So you'll notice we get our 3 different zeros. That's where we're going to cross that axis. And if we have those 3 zeros and maybe the minimum and the maximum, right? If we used our calculator to do a little left bound, right bound, find the minimums, find the maximums, those are what we call sufficient points, right? Technically, the min and the max are the turning points. They're also sometimes what we call the extrema, right? Or the extremes of the graph, the extrema, right? So that's not the degree. The extrema are the turning points. And again, other points could help as well. If we plug in 1, it looks like we're maybe up at about 8. You know, if we plot a few extra points, we can just make this thing look a little more accurate. Okay? Hopefully that reminds you of quite a few things that we can do with polynomials, though. One last thing to talk about before we go back for that initial problem is the multiplicity. Multiplicity is, again, going to come down to those factors. So you'll notice this x plus 5 is to the first power. X plus 2 over here, though, is squared. And x minus 1 is cubed. Well, let's take a look at all the zeros. Again, this would have had a 0 at -5. And notice the 0 over here at -5, the line just crosses directly through our 0. Well, that's because it was of degree 1. First degree is sort of linear. Imagine it's going to cross through there in almost a straight line, right? It's always a curve on a polynomial, but it's just sort of crossing straight through, no fanciness. But now if you notice at -2, right, for x plus 2 squared, at -2 you'll notice it didn't cross through. It sort of bounced off of there, almost like a polynomial would, right? A quadratic would. It just bounced off the x-axis. And that's where we say it counts for 2, because of, again, that squared exponent. It counts for 2 of our zeros, right? Because if we count up the number of x's up here, we've got x to the first, so that's 1. X squared, so that's 2 more, so we're up to 3. And you'll notice the last factor, again, cubic, technically, I would say this is of degree 6. And you notice if you look down at our problem here, degree 6 would make sense. Both ends are going up. It's an even function. I also have 1, 2, 3, 4, almost 5 turning points. But again, not quite, because this one's going to be a little bit fancy over here at +1, right? Because notice again, third degree, it doesn't just cross through, it doesn't bounce off the axis. We definitely went from negative to positive. But notice it sort of looks cubic, doesn't it? It's got that little bit of an S curve to it. So if it's third power, it's going to do sort of that swooping, right, through the axis, kind of an idea. And again, if it's any other even exponent, such as that squared that we had, that's going to be a bouncing, right? It's going to be sort of that top or bottom. It's that even idea. And any odd exponent, again, crossing with sort of that odd S-curve idea. So let's go back to our original problem that we skipped over, and let's real quick see if we can't make a fast sketch out of this. end behavior, again, I'm going to count up my x's. 1, 2, 3, and 4, 5, 6, right? We've got that third power up there. It looks like we're going to be of degree, right, 6 again. So I expect my end behavior to go the same directions, right? Either both going up or both going down. And again, a positive leading coefficient, that 2 out in front. So therefore, I would expect both ends to be going up, right? Now, I need something to connect those two. So now let's go ahead and jump to the x-intercepts. We know we're going to have x-intercepts of, well, hey, at x squared here. So that's going to be 0, 0. And notice that it's a squared, right? If I plugged in 0 for x, though, it's going to turn the whole thing to 0. But squared means that's a double. So again, I'm going to make a little bit of a note as far as multiplicity goes, right? That one's going to be a double 0. So it's going to bounce off that axis. Again, we're also going to have a 0 at -1. But notice it's just a single. It's just to the first power, right? And then we also are going to have an x-intercept at +4. Because again, that's that last factor. -4 would have been 0. But notice that one's also cubed, so I would say that's a triple 0, or it's got multiplicity 3, right? So multiplicity here would have been a 1 right in the middle. So again, let's plot those zeros. 1, 2, 3, 4, 0, 0, and again at -1, 0. Well, if this is my last 0 way over here at the right, and it's a triple 0, I kind of expect this line to drop down through here, but kind of do a little bit of that S-curve idea, right? And I'm going to overemphasize it. It might not look that drastic if you put that on your calculator, but we want to make sure we emphasize that's going through there like a cubic function. Then notice the distance to my next 0 is pretty far away, right? 0 all the way to 4 compared to 0 to -1. So how this loops down, it should actually drop down pretty far before it comes back up. Right? It's going to have a pretty drastic drop. Now we'll show the difference there when we get to the next one. Again, the double 0 was 0, 0. So that's going to kind of jump through there. That's going to be that bouncing 0, right? We're going to not cross through the axis. But now I need to loop back around again. I need another turning point because I need to get back for that other 0 at -1. So I'm going to drop down here, do a quick turning point. Again, notice I didn't drop as far down because my zeros are closer together. And then that one's going to take off going upwards, right? We said they both finish going up. So we've got that set. Extra values, we could have maybe found this minimum or found this minimum, maybe put some scale on our y-axis. But overall, I would say that's a pretty good sketch. It gets our x-intercepts across, although I should probably label there. It shows us a little bit of the size of, again, the highs and the lows. It showed us those x-intercepts and their multiplicity. So again, I hope that helps you graphing, or at least making a quick sketch of a graph. Maybe a few extra labels wouldn't hurt. Maybe going over here, and calling that -1, just so we've got a little extra label going there. Always a good idea. Good luck graphing, and if you have any questions, talk to your teacher. Otherwise, have a great day.